All right, chapter 12, section 1. What you see here is actually something called peat man. This individual died around 350 BCE, and he died in something called peat moss. Peat moss is an organism, it's a pretty simple organism. It's used as a fuel source, it's a good carbon sink. In other words, it eats up a lot of carbon and it preserves organisms like this guy. You can see the wrinkles on his forehead, the wrinkles in his eyes. You can see a lot of features on him, which is kind of neat. And is a famous fossil that was found some years ago. And to get opener into this idea of the fossil record. Now, the fossil record is literally the record of all the fossils that exist on Earth. And how fossils are made will give you an idea of whether or not they're made. So, for example, uh, a fossil can be made when minerals replace hard structures of the dead organism. So water will come in and bring in some minerals. The minerals will replace and deposit where hard parts of the dead organism lay. So here you have the jaw and neck of some dead organism, and they'll replace some of the living tissue with minerals that last a lot longer. Uh, Sometimes you get water that will remove the original tissue and it'll leave an impression. So it won't necessarily remineralize. It won't bring in minerals to replace the matter that was there, but instead will leave an impression and form like a cast, like an outer shell of what the organism used to look like this. Sometimes you can record an activity, whether it be swimming or fertilization, etc. Like in Jurassic Park, sometimes it's preserved in amber, and you can actually see tissue from the organism long after the tissue would have rotted away. It's kind of neat. And sometimes it's frozen in ice. Like this individual was frozen in ice, and from here you'd be able to figure out how old or how young that fossil is. Sometimes you'll find a fossil and it's only a few years old. Sometimes you'll find it's a few hundreds of years old. Uh, Not everything becomes fossilized. The best way to describe what becomes fossilized is hard parts, lots of organisms, and over a large area. So if you're made of soft spots and you are in an area that's in one specific spot but not all over, chances are we're not going to find you. So hard stuff, you have to have hard pieces. You have to be dispersed and lots of that organism, not just a few of them. You need lots and lots of them so that when we're digging through, we just so happen to run into you. And then being bigger helps too. Very few of the things that were alive ever become fossils, and even fewer of those are ever found. Now, once you find a fossil, figuring out how old that fossil is creates its own problems. You can figure it out based on the banding pattern of the rocks. So when you see this similar banding pattern in other places, you know that they were fossilized around the same time. You can also use radiometric dating, which lets you estimate the age of a rock based on how much radioactive material is left over from that rock, and that's a good way of measuring. But it's also a when I say it's a good way, it's also inaccurate in such that it gives you a range. It doesn't give you a date. So, for example, carbon 14 is a great radiometric dating device. What is carbon 14? Carbon 12. Okay, this 12 is the number of protons and neutrons. Carbon has six protons, so carbon 12, if it's protons plus neutrons, and it's 12, and it has six naturally. Six plus what gives you 12? That's six. Carbon 14 is six plus what gives you 14? That's eight. Slowly over time, carbon 14 becomes carbon 12. It takes a while, but it does it. It takes tens of thousands of years. So if you find something that's dead, that's within tens of thousands of years, you can use carbon 14 to date it and figure out how old something is. These are isotopes because isotopes of an atom have a different number of neutrons than the normal. Okay. The half life of an atom is the amount of time it would take for the radioactive aspect of an atom to decay. So let's say you have 100 grams of carbon 14 after one half life, right, which is 5,730 years for carbon 14. Half of the carbon 14 goes away. So at around 5,730 years, instead of 100 grams, you'll have 50. Then at 11,460 years, you'll have half of what's left. Half of a half, which is a quarter. And then after another half life, you'll have half of what's left. Half of a half, half of that. Right? So then you're at an eighth, and then you're at a 16th, and it kind of keeps going this way. And somewhere around 60,000 years ago, it no longer is accurate. Okay, and this is really good. Now, for carbon 14, the half life is 5,700 years. For other radioactive elements, the half life can be millions of years. Okay, so and then if you are millions of years half life, it's less accurate, but it can go further back. If you had a half life of a minute, then after 2 minutes, right? At 1 minute you have half. At 2 minutes you have half of a half, which is a quarter, etc. And that's it for chapter 12, section 1.